get that in picture?
Okay, so you have a beam here that's simply supported with a load. There's a moment on the sides. You take the moment, you multiply it by the centroid and multiply it by the second moment of area, which we can call the moment of inertia, and it gets the maximum stress that this beam is experiencing, which you need to know in order to design the beam. Another example of a use of moment of inertia has to do with mass. Bicycle wheels. Traditional bicycle wheels had spokes. There are ones now you see over the past 20, 25 years that have discs. The difference between this is the distribution of the mass. Most of the mass is out here. Here, the mass is distributed more evenly. Excuse me. The moment about any point is equal to the moment of inertia. And which second moment am I dealing with here? Second moment of mass or area?
Area.
Mass. It's the distribution of mass times its angular acceleration. And the third example, again, you'll see this in junior level classes, is column design. You have a column, it's subjected to what kind of loading? Compression. If it's very slender, it's gonna buckle, and the critical stress that's being applied to decrease buckling is pi squared times E, which is modulus elasticity. Those of you in materials took it know that. L is the unsupported length, the length divided by, this thing is, it's a function of the second moment. Radius of gyration. So this K is a radius of gyration, and you calculate that based on moment of inertia. So if the L that you calculate is greater than the L if the length of your beam, of the column is longer than the L you calculated, you know that there's going to be buckling. So you have to make sure that you stay below the L you calculated. So these are uses for moment of inertia. Both moment of area, because this has to do with the area. Notice, I could have a beam that's square or rectangular. I could also have, what's this called? An I-beam. The distribution of its area is different. That's going to control what the moment of inertia is. So this one's based on second moment of area. This is based on mass, second moment of mass, and this is based on area again. Okay, so these are some uses. But now we have to be comfortable calculating them. And it's kind of a pain. But you're going to do it so much, you can have everything memorized. So, let's make sure that you're comfortable. So let's do this. Okay, there are three scenarios. I have some body, and this is where its center is. Actually, two scenarios. This is the x-axis. And let's call this, instead of G, let's call that C for the center. And we call this x sub c because it goes through the center. And then this is x prime. No, let's call it x. You can't see it. Can you see it now or no?
No.
Barely. It doesn't really matter where it is as long as it's not going through the center of the body. Let's just call, did I say x?
X prime.
No, you said X.
Let's call x. So, tell me about this axis. What is this axis going through?
The center.
It's going through, and let's just call it center, because we don't want to say it's going through the centroid because maybe we're dealing with mass. We don't want to say the center of mass or center of weight because maybe we're dealing with area or volume. So let's just say it's going through the center. And what's special about this? It's not going through center. That's it. We're interested in learning more about this body. We want to find its moment of inertia. We want to find the moment of inertia of this body. But in order to find the moment of inertia, don't I need to know a distance? I need to know the distance and axis to find the moment of inertia about, right? Because remember, the second moment of area, the second moment of mass, it's the x times the area times another x. I need to have a distance. It's like moment. Think about moment. We know what moment is. Moment is something times a distance. I need to know a distance. So in order to find a moment of inertia, I need to know, am I trying to find the moment of inertia about this or this? Okay? It doesn't matter. I could tell you, I could say find the moment of inertia of this body around here, or find the moment of inertia about this body around here. Okay? So now let's take a look at this sheet. We are going to cross this whole column, because we're not going to memorize that. So just cross it out.
Can you use those?
Nope. We are only going to know these.
Those are for the center, right? That left column?
That's
In
right.
the video you said?
Yeah.
Yeah.
So does everybody see how this column, the column that I just circled, let's take a look. Maybe we should use the same, let's use the same notations. Could everybody come back here? Let's use the same notations that the textbook has. So that means that an x represents the axis that goes through the center, and x prime represents the axis. So axis through center, and axis not through center. So if I have a rectangular body and I want to find the moment of inertia about the x-axis, what equation do I use? pH cubed over 12. What's B represent? The base, and what's H represent? The height. How about if I wanted to find the moment of inertia about y, the y-axis? What equation would I use?
The same thing, but H.
Yes. So I would use the same equation. Now in statics, they don't make the equation H cubed B. They don't say H times B cubed. What they do is they just rotate the picture and say, oh, well here's my base and here's my height. So it's the same equation. Did everybody get that? So when I'm trying to find the moment of inertia about x, it's B. So actually we should probably not put this here. Or we could say this is H when we do y, and this is B when we do x, and this is H when we do x, and B when we do y. Or you don't really, just don't put B and H. This is the equation. Okay, what about a triangle? What is the moment of inertia about the x-axis? pH cubed over 36. How about moment of inertia through the center of a circle? Pi r4 over 4. You agree that this is all second moment of area, right? Right? Because why is it area? We're dealing with two-dimensional pictures, and it's all based on distances. It's based on its geometry. So we could write moment of inertia because we've learned that we could use the word moment of inertia for this also. Now go on the other side of the page. Now it's called moment of inertia. Look at these equations. What do all the equations have in it? Mass. So we're dealing with second moment of mass. Let's look at the slender rod. when they want to find the moment of inertia about the x-axis through the center along the axis of the rod, what is the moment of inertia? 0. Because it's considered very slender, there's not enough material above and below. Let's take a look at this one. Do you see the circular cylinder? This one has more material, right? So the moment of inertia about x is 1/2 mass times the radius squared, because now we're dealing with more material. The more material, the more mass to swing, the greater the moment of inertia. Okay, let's go back to the slender rod. The moment of inertia about the z-axis is 1/12 ml squared. And how about for the circular cylinder? The moment about z is 1/12 mass, the radius has to come into play, the 3r squared plus l squared. We can derive every one of these equations. Do you guys like deriving things? I really don't, but maybe some of you do. And I did do some derivations using integration, but we don't have to do this. We just need to know these. So, do you like memorizing? I don't. These are going to become a part of you. You're never going to have to memorize them. I know them now, and I took statics while I've been teaching it, so it doesn't count. But it's like knowing the area, the how many feet are in a mile. You just eventually know it because you used it so much as a civil engineer. You guys are going to know these by senior year. Some of them you're not going to use that much, but you're going to know this one and you're going to know this one, whether you want to memorize it or not. Right now, what do? Put them on your cheat sheet.
Maybe on the final, but not on first.
Right. So this is kind of, remember you said you like watching the videos, but then you will kind of want a short summary, and this is the summary. So now what I would like to do is look at some homework problems. We're dealing with composite body. Oh, no, I didn't do this one yet. We have to know how to do this. So whenever you have a situation where the axis is not going through the center, you deal with the parallel axis theorem. Not a problem. I sub x prime is equal to I sub x plus right, y bar times, we're dealing with second area squared.
It's not y bar squared, Harry?
Thank you. Okay, so that one I guess I didn't memorize. So what does y bar stand for? Y bar is the distance, the perpendicular distance between the center axis and the axis in question. Which means the further the axis is away from the center, the greater moment of inertia. So let's look at the first problem. What's the first homework problem? 33. 31?
Yeah.
Okay, chapter 10. Even though this is really one piece of material, we can divide it up into two. So it's saying locate the centroid x bar of the cross-sectional area of the angle bracket, and then find the moment of inertia about y prime, about the y prime centroidal axis. So even though it looks like a 3D problem, they're really only asking you for it in terms of a 2D problem. Why?
Didn't care about the area. Two-dimensional area.
Well, it's two-dimensional, so they would care about the area.
Yeah.
They're not giving you any z directions, right? They're only giving you x and y. And notice they cut the back part off. So we're really only looking at this. Okay? We're only looking at this L right here. Now, how did you divide it? You could either divide it like this, or you could divide it like this. So what did you guys do?
The second one,
This here?
yeah. We had two at the same time.
So here's one body and here's the other body. So we have two bodies on here, 1 and 2. So all these problems I do in tables. So, the section, so are we trying to find second moment of area or mass? How do you know? They don't give you mass. So the critical component is area. What's the units of area? Inches squared. We have two sections, right? Section 1, which is this one. And then section 2, which is like this. And let's just write the dimensions so we remember. 6 by 2, this is 6 inches, 2 inches. And this, Chelsea, you said it was the same?
Yeah.
Okay. So what's the area of the first one? 12. Do I have to write inches squared? No, because I wrote it at the top of the column. There's 12. So what am I interested in finding? They want to know what the centroid is, right? So they want to know x bar. What's the units of x bar? Inches. Where are we measuring things from?